everything okay? Sorry for the late. A great honor to be that here we are in this moment, Mr. John Byrne from US. I think so. Very interesting presentations coming. I suppose you heard about the titles that climate change and China and sustainable development. My name is from the Climate Change Council at the University. The Climate Change Council is the first university council in Hungary, which developed by the different Szent István University professors. This council invited Mr. Byrne to take a presentation, and the topic in this day connected to the sustainable development and different challenges, how we can build up a future here in Hungary, in Europe, in China also, and we get some information about the US aspect of this climate change effect, and maybe heard about it. Mr. Byrne, Professor Byrne, is the director of the Center of Energy and Environmental Policy in Gödöllő University, and member of this Nobel Peace Prize team at IPCC, and he has a little different titles also, but I don't want to say at least the titles. I would like to ask Mr. Byrne, Professor Byrne, the floor is yours. Please start your presentation today for us.
Thank you very much for that kind introduction. I'm very happy to be here. You have wonderful weather. I've come from a very rainy and windy and difficult climate right now, and so I'm very happy to be here with such wonderful sun and pleasant temperature. And so it's not clear that we will always have this kind of wonderful weather in our futures, but it's very nice to have today. So. I am going to try and give you a sense of what we understand about this climate change process. As you probably are aware, climate change is really a matter that could only be discovered with research, with science. We wouldn't know about climate change if it wasn't for science. And we wouldn't know how to act on this problem if we didn't have some sense of policy and economics. So it is really an interdisciplinary challenge, and all people with brains are needed to try and find the solutions to this very difficult problem. So I'm going to begin by giving you a sense of how it is that human beings could actually affect climate. Sometimes I think even researchers and scientists can have difficulty believing that we could change climate. So I'm going to try and give you some small portrait first to understand, then I'm going to show you some of the basic scientific findings so far and what we can expect for our future, and then I'm going to offer what would be practical steps that we could all be taking together to address this problem. I don't have China directly in this talk, but we have done a lot of work in China. China is now leading, as you will see. I do have something a little bit on China. They are leading in the shift to a low-carbon economy at the same time that they are moving on a high-carbon economy. So they're sort of both at the same time, and so I'd be happy to talk about particulars if you have questions about China. So. Let me begin to give you a sense. The intent here is to give you an idea of how human beings could have actually changed the climate. And even if you have studied the science, I think it's still hard for us sometimes to recognize that we could actually have this effect. So I'm going to take a simple example, one particular technology, and what we did with that technology over the last 100 years. That technology is electric light. And I'm going to try and show you from that how we can have a global impact. So, to begin, if this works, yeah, let me remind you that at night, human beings mainly received light from two sources. One was from celestial sources, from sunlight bouncing off moons and from starlight. And then we had invented a very interesting, well-performing technology still to this day, a liquid fuel lamp on your right-hand side. And this was pretty much how we had light at night for most of human history. But in the latter part of the 19th and beginning of the 20th century, the electric light came forward. And that electric light changed how we receive light, both in buildings and outdoors. In fact, the street lights on the right are so effective in providing low-level scatter that often you cannot see starlight at night. Our low-level electric light can actually push out the lighting coming from stars at night. And this simple technology made a way of life very possible that one could not have imagined at the beginning of the 20th century. So I'm going to take you first to my country, to New York City. This is a famous area in New York called Times Square. This is at the end of the 19th century, and then as you go around, is New York City the exact same location, its transformation in 100 years. So we went from a city that was dark at night, at the end of the 19th century, except for those small liquid fuel lamps, to a city that is now lit up all the time. And in fact, it has a brightness, if you visit Times Square, that it's almost impossible to believe that it is night. There is so much light scattered on the street during the evening. This way of life, where we went from very little use of carbon-based fuels to a very intensive use of carbon-based fuels, created an entirely different society in just 100 years. And this city, you know, and you can see a similar change in Budapest in the same period of time. You can try and find at the end of the 19th century a picture of Budapest at night. It is very difficult to find. But by the 1930s, this icon of Budapest and both the bridge and the palace became places to showcase the use of this technology, electric light. Still, the moon is in some ways the more dominant source of light in this picture, but you can see something of a change happening. And now today, Budapest is lit up in the same way that New York City is. And it is actually, you can still see the moon, but you cannot see too much starlight most times in the evening in Budapest. And that's an indication of this change in the way of life toward one that uses an awful lot of electric light, and behind that electric light is our power plants, and behind those power plants are fuel sources that make possible the delivery of that electric service. I would say that both in Europe and in the US, this transition took approximately 100 years. And now we will go to another place where things are happening much faster. So this is Chang'an in Beijing in 1949. In 1949, Beijing was still largely a city that was dark at night. I'm now going to show you the exact same street today. Yeah. So in 50 years, the city transformed its way of life. Critical to that transformation is the utilization of these technologies that are fossil fuel, largely fossil fuel based, for that purpose. So how big of an impact has this had? Human beings using electric lights out and about in the world. NASA, a few years ago, took pictures from satellites of the same hour of the same night, and then stitched together these pictures to make one complete picture of Earth for that single hour of night. I don't know if you can see so well because we still have sunlight in this room, so but you may notice that in North America, in Europe, along the Gold Coast of China, Japan, South Korea, the eastern coast of Australia, South Africa, the coastal areas of Latin America, you can see this extraordinary amount of light being cast by human-made technology at night. This is light-sensitive photography, not heat-sensitive. And it gives you an indication, if you consider, if you were a planet near Earth, and you had been watching that planet Earth for a long period of time, you would notice that in 100 years, something had happened. That something is that human beings took over a development model and spread it through not all of the world, but through parts of the world. And that now we have a global impact on that light scatter that was never seen before in cosmic history. That is, what you now see as Earth can only have been seen in the last 50 to 30 years. And it is because of human activity. This human activity is what is behind the challenge and the problem of climate change. Every pixel of light that you see there has to have an energy source to provide that light. That energy source is primarily fossil fuels. Those fossil fuels, when burned at power plants to provide electric light, release gases into the atmosphere, and the release of those gases into the atmosphere has an effect of trapping both light and heat on the surface of the Earth. So this is my simple way of saying, before I get into the science side, my simple way of saying human beings, unbelievably, had an impact that is planetary in character. And now let me give you some of the underlying science on what has happened. So, I'll begin with the chemistry. The atmosphere's chemistry has been changed since especially the end of the 19th century. The array of gases that are found in the atmosphere have been transformed by this new development way of life that you found in the 20th century. These gases, carbon dioxide, methane, nitrous oxide, these three are gases that are released from chemicals that only human beings have made. They are not found in nature. These are the chlorofluorocarbons, which are used for solvents, for refrigerants, for other purposes. They are human-made chemicals, and they've only been around for a short period of time. All of these gases, in different ways, trap heat on the surface of the Earth. The most important by volume is the first gas in the first column, carbon dioxide. We have transformed the concentration of that gas in the atmosphere from roughly 280 parts per million for several 100,000 years to, in the last 50 years, concentrations that are in the area of 390 parts per million by volume. That's a big change. To give you an idea, I mean, the numbers by themselves may not give you a whole lot of understanding, but our planet can absorb carbon dioxide through oceans and land-based materials, all that vegetation, the green materials there, can take up about the oceans can take up about 2 petagrams of CO2 a year, and the Earth's surface, the terrestrial surface, can take up also about 2 petagrams per year, so that's 4 petagrams. 100 parts per million change in CO2 is 200 petagrams. So we are releasing at a rate of 200 petagrams, and our planet can absorb 4. We are trapping a lot of those gases as a result in the atmosphere because we do not have the ability, the planet itself does not have the ability to recycle. It's this trapping of these gases that create this warming effect that is the most serious problem in the climate case. And this row here on atmospheric lifetime, the molecules that we release stay in the atmosphere, or the interchange between the surface and the atmosphere. It takes roughly 50 to 200 years to rebalance that CO2 that we're putting in the atmosphere. So, in practical terms, when we first made steel in Manchester 200 years ago, you can still find the effect of that decision by the CO2 that was released from steel manufacturing. That means that this is a long life problem. Even if we start today to dramatically reduce CO2, it is going to take the better part of a century before we're going to see the effects in terms of the atmospheric chemistry. So this is a long life problem. It is, no matter what we do, it is going to take a long time for it to be resolved. And human beings are not well known for their ability to solve long-term problems like this. Basically, certainly my generation, I'm going to leave the Earth soon, and you're going to be left with the 100 years of... all of that is something that we have to still make a commitment to, even though I will never see the benefits of the changes that we make in my lifetime. And you will not see very many either. It is for the great-grandchildren that we are now acting, because this problem, just in terms of its chemistry, it will take the better part of a century to resolve. Warnings about what it means to store that much carbon dioxide in the atmosphere can be found in our poles. The Arctic and the Antarctic areas are obviously the coldest parts of the planet, and the greatest rate of change in temperature will occur first where it is coldest. So you can see the effects that are now happening of this storage of all of these greenhouse gases, particularly carbon dioxide, in the atmosphere. You can see it in Antarctica and the Arctic. So first I begin with Antarctica. This is the Larsen B ice shelf on the western edge of Antarctica. This ice shelf is an enormous body, partly connected to land, partly in the sea. And I'm going to show you what happened in this area in just 6 weeks. 6 weeks. So we're going to start the end of January. This is the end of February. You can see the Arctic, the ice shelf beginning to break up in the Antarctic. 2 weeks later, this entire sheet of ice has completely broken up. Sheets of ice advance and retreat in the Antarctic all the time. There's always melting and freezing. But an event of this scale, this is, in terms of an area, this is an area about 1/3 of Hungary that has now gone from a solid state to a liquid state. This kind of change is happening rapidly in the colder parts of our planet. We don't really understand how to explain things that change this fast. The modeling that we've done is not built to explain fast change like this. It's really, climate models are mainly meant to explain several hundred thousand year cycles. So events that take place in 6 weeks, they're a bit beyond what the models were originally created to predict. Changes are happening faster than what we would normally understand. The same is true in the Arctic. This is the Arctic Sea, which is mostly ice during its winter. I'm going to show you what's happened in 30 years. We'll go here in a moment. This is Greenland, but the ocean itself here, the sea here, that has a great deal of ice in it. This is 1973. 30 years later, the Arctic ice is now 30% less than it was before, and 60% less by volume. So it means that an ocean, now we're talking something much, much bigger than Hungary. This is European scale, that we've basically removed 30% of the ice by area and 60% by volume in 30 years. This kind of effect, very quick by most analyses, is difficult to explain unless you introduce that 100-year period where human beings changed the development model, and when they changed the development model, stored so much of CO2 in the atmosphere. The most worrisome part of these effects is in the Antarctic. The Antarctic is a land surface with about, about 3.5 kilometers high of snow. 3.5 kilometers high of snow. The orange area is the normal melt that would occur during the warm season. So the orange is the exposure of land beneath the snow and ice during parts of the seasonal cycle. This is 1992. This is 2002. And this is 2005. Again, the basic models for prediction don't help us here. This is much faster change than we would normally anticipate. This has an additional feedback effect. When you melt back the snow and ice like this, you expose the tundra. The tundra is dark, so it can absorb the sunlight and store it. That is, this area now becomes warmer, which actually creates a feedback of warming the surface of Greenland, thus causing even faster melt. The difference between this issue and the two others that I mentioned earlier in the Antarctic and the Arctic, this is water that's on land that's now heading into the seas. As we melt this water into the seas, you're going to see sea level rise. So this is a particularly worrisome problem from a research point of view, and we are still trying to figure out how fast this kind of change might come in the future. When we try to model temperature changes against the storage of greenhouse gases in the atmosphere, we get a graphic like this. This comes out of the Intergovernmental Panel on Climate Change's fourth assessment. And what I want to draw your attention to is that these temperature bands are based upon our best available data on how much temperature varies over this period from 140, 150 years. This red line is what the rate of temperature increase looks like if you put it over the whole 150-year period. This purple line is if you are over the last 100 years. The orange is over the last 50, and the yellow is over the last 25. It would appear that the impacts are increasing at an increasing rate. That is, temperature effects associated with our activity are now increasing at an increasing rate. Our best available models indicate the following. I'm going to now give you, I'm going to stop telling you, bad stories in a moment. I'm going to get to what can we do about this in a moment, but I think it's important that you at least understand the scale of the issue that we're dealing with. So I'm going to now use some modeling that's been done again for the Intergovernmental Panel on Climate Change on two scenarios. One scenario is that we essentially don't change our behavior. We stay with that development model and we continue to release greenhouse gases at the rate we're now releasing them. And the other is that we are going to reduce those releases over the course of the century at a level that is about equivalent to 450 parts per million. That is, we're going to go above what was the 280 parts per million that was the pre-industrial era. We're going to go to 450, but we're going to try and level that off in this 100-year period. Many argue that that's not enough, but I'm going to try and show you that even if we try to do 450, it's going to be really, really tough. Okay? So I'd like to show you what the world looks like in those two scenarios, one where we don't act and one where we do act. So on your left-hand side will be the case of our planet where the relative temperature changes are if we do nothing, and on the right is the relative temperature changes if we act. And we act to get it down to 450 parts per million, which is really hard to do, but I'm going to try and... By mid-century, you can see if we stay with the business as usual scenario, if we don't act, you can see warming occurring. You can see that essentially Europe will be transformed agriculturally, in terms of what species, both fauna and flora that thrive, will be radically transformed by mid-century if we stay with business as usual. If we begin to make changes, Europe will still be affected, particularly Central Europe is still going to be affected to some extent, but the effects will be far less severe than what would happen if we fail to act. And by the end of the century, North America, where I live, will be utterly transformed. North America will no longer have significant cold seasons. The impacts will be dramatic, and the impacts in the case of Europe are equally strong. You can't see it as well here because this particular rotation for the model features North America, but there's just tremendous changes in Europe as well. On the right-hand side, you can see by contrast, there is a significantly different world in the future, one that would not be terribly different from the one that this century began with. So the choice between the two is pretty dramatic. It's one where we will have a lot of warmth in the atmosphere and a lot of volatility, a lot more storm activity, a lot more floods and droughts, extremes of weather on the left-hand side, less of it on the right-hand side. I just want to mention, because you're here in Hungary specifically, but in Central Europe, there's a particularly important aspect to this problem having to do with water, because you retain a great deal of water that's very important for this region. And the impact, the interaction between climate change and water quality is a very important one that you have a particular stake at. In the case of the US, we have these very large lakes on the northern border where also this problem exists. When we find contaminant in our water supply, the contaminant that comes from our activities, about 60% of that contaminant comes from storm vents. That is, most of the contamination in the water supply comes from storm events. If you increase storm events, you are going to increase the rate at which that contaminant makes its way into water supplies. The best projections we have now is that storm events are going to increase somewhere between 10 and 40%. So that means that our ability to provide drinkable water, or water that can be used for a variety of human functions, will become more and more problematic as we move into this new century, unless we take action to slow down this process. And I think that's a really important issue for this region in particular. I understand that you had a very dry summer, and that the Danube did not have the kind of water volume that is typical, and this kind of problem could be a very serious problem for this region if we don't take care of this. And oddly, how do we get the contaminants out of the water supply? When we have contamination in our water supply, how do we get it out? We clean it. And how do we clean it? Exactly right. And how do we clean it? We use a treatment plant, right? And how do we power the treatment plant? Chemical and biological. And behind that will be an energy system that is pumping all. So you are actually returning the gases to the atmosphere as part of the process of trying to clean the water. So we're caught in a feedback that could be problematic for us going forward into the future. Okay, so yeah, it's a big problem. It's a serious problem. It's going to fall more for you to experience, the younger members of this audience, than for older people. A lot of the uncertainties and difficulties will come in the next 20 to 50 years. Against that portrait, what can we do to solve this problem? Actually, the work of the Intergovernmental Panel on Climate Change has looked at this question carefully. There's a working group, Working Group 3, that I work with, that has been working on this problem. What can be done over the last 20 years? And actually, we're fairly confident that we know what needs to be done. If we're to get to a point where that 450 parts per million is possible, we're going to need to get rid of about 23, 24 gigatons of CO2 by 2030. And the tools, based upon economic analysis of what is the most cost-effective and comes from technologies that we already know how to deploy, what would be the most effective way to get there? Most of it, about 51% of it, is through energy efficiency rather than having to invent new technologies. We waste an enormous amount of energy in industrial society, in our buildings and in our transportation systems. Getting at this efficiency is perhaps the most important thing that we can do. And one of the great advantages of this particular item and why this wedge is so big is because getting rid of the inefficiencies actually will lower your energy costs over time. It's one of the few cases in the climate change debate where you can have an economic benefit as part of the process of trying to solve this problem. The second major area is going to come in transportation planning, land use planning. Europe is way ahead. Asia is way ahead of North America in this area. Frankly speaking, North America is going to have a difficult time competing in a low-carbon future because we are really bad at this. We ride around in cars everywhere. We have our cities spread out. Europe and Asia are better models for this purpose in using public transit and having cities that are more compact. This is going to play a really important role in the first part of the 21st century. Renewable energy, the shift to entirely no-carbon opportunities will play also a very important role. It will be smaller in the beginning because right now renewable energy is more expensive than other energy sources, so it's hard to get it into the marketplace fast. But this will become an increasingly important role as we move out toward mid-century. And then, even with all of that we know how to do, we still need some improvements in technology in the future. This is a debating point, this final wedge. I'm not convinced that carbon capture and storage is going to be viable, and I don't think new nuclear power plant designs will be viable. I'd be happy to talk about that because I know that Hungary depends on a lot of nuclear power, so I'd be happy to talk about that as we move along. But what I'd like to suggest to you is the major factors are in improving efficiency and in organizing ourselves so that we use less energy in our daily activities. Okay, so let me now give you a basic example of the kind of problem that we're going to face trying to get there in this century. This is a graphic using an economic methodology called the Gini coefficient and Lorenz curve, and basically it's an effort to define what is the burden of a population on an impact. For this case, affecting the amount of carbon dioxide that's released into the atmosphere. The black line says that the proportion is equal across populations of the planet. 20% of the population accounts for 20% of the carbon dioxide, 40%, 40, 80%, 80, okay? That's not the way the world is now organized. There is a very small portion of the population that is responsible for most of the carbon dioxide emissions. That is North America, Europe, Japan, Australia, and New Zealand. The largest part of the population, Asia, Africa, and Latin America, are not responsible currently, have not been for the last 50 to 80 years. But the point that I'm going to give you in this example, this is an analysis to say, against that goal of getting to 450 parts per million, through the end of the century, we would still have some inequality. Some parts of the world would still be disproportionately responsible for the release of CO2. But 450 parts per million will get you somewhere closer to a more equal state as we move forward into the 21st century. As you know, there is an international treaty. That international treaty has a protocol called the Kyoto Protocol, which expires next year. It is the only effort so far for all of the world to cooperate in reducing these gases. There is one and only one country that is not currently acting on that protocol target. Yeah. Yeah. If the U.S. remains outside of that treaty framework for another 15 years, our, what happened there? There we go. This is the red line. If the U.S. stays out, the world will be more unequal because the U.S. will continue to emit disproportionately against population. And the lowest that we can get if the U.S. stays out 15 years is 461 parts per million. I know that's a lot of numbers and a lot of chemistry, but the point to you is that if the U.S. does not make changes, it's really impossible for the world to avoid climate change of a more significant kind in the 21st century. So the pressure is very significant on the U.S. The pressure is also very significant on Europe, Japan, Australia, and New Zealand. They are the so-called Annex I countries. The non-Annex I countries of Latin America, Asia, and Africa are demanding that these countries make significant changes as a condition of moving forward. So far, that treaty process is not accomplishing much. COP15 in Copenhagen, this is the conference of the parties negotiating that treaty, came up with very bland policy statements. They agreed to recognize that there is a scientific view. That's better than some of the politics in my country, which are still denying the scientific view. They agreed to try and monitor and verify policies that attempt to reduce CO2. And they agreed that we should all be committed to implementing actions to reduce CO2 emissions. But there's no obligation, there's no penalty if the obligation is not met. Last year in Cancun, we didn't do much better. In fact, we did in some ways worse. In Cancun, these events cost a lot of money to stage. Last year, we agreed that probably what we're doing so far is not what is required, but at least it's a new beginning. This is 12 years. This COP16 means the parties have been meeting for 16 years. For the last 12 years, we've had a treaty obligation, and yet we have made no significant improvement over that period of time. So that's the dilemma. As long as the U.S. stays out, I think these treaties, we're going to have another event in a couple of months in Durban, in South Africa. I think that the chances of anything happening significant in Durban are very, very small. I think Europe will try to insist that some kind of continuation of the framework be voted, but I don't think there's going to be anything significant beyond this sort of bland rhetoric. So, what do we do to start making significant changes? The European Union and the US have two basic strategies. The European Union has, and I congratulate them on one level for it, they have put up a trading scheme that at least puts a price on carbon. The US has no national price on carbon. Without a price on carbon, it's very difficult to discourage the release of the CO2 in a systematic way. So the EU has taken an important step that way. The EU has also published its Roadmap 2050, requiring that all member states come up with efforts to get to 80% reduction. 80% reduction gets you to 450 parts per million. Okay? So EU has had a strong top-down, but as you are probably also aware, the trading scheme has not exactly reduced CO2 emissions in Europe. There's a lot of money that's been made in trading carbon allowances in Europe, but it's not clear that very much reduction in CO2 has occurred. Similarly, a 2050 goal is a very welcome goal to political systems in Europe, because no one is going to be held accountable that makes the statement today that I'm in favor of an 80% reduction by 2050. So there are some problems with that. The US has followed a different policy. It is more bottom-up. Our central government is not setting the rules for the pursuit of these kinds of ideas. Instead, it's being left to localities to figure out what to do. There are problems with this approach too, because it means that there is no national commitment, only whatever is being done at the local level. However, I think there are some advantages that have been found in this regard. So I'm going to focus now on the US because that's what I was asked to do, and then I will talk to China at the end if you want to talk on China. So where is there a glimmer of hope that the US is actually serious in doing something? If you look at our central government, it doesn't look serious at all. It doesn't look like it's at all committed to making these changes. But if you look at our localities, you get an entirely different picture. If you want to sell electricity in the United States, 37 states out of the 50 in the United States now have a restriction that in order for you to sell electricity, you must have a certain percentage coming from renewable energy sources. About 75% of the economy and a little bit more of the population now live under rules that require a shift toward renewable energy sources. You won't find that when you look at the central government policy, but if you try to act in the US, you will find local policies that will require you to meet these goals. Interestingly, these commitments have penalties. If a company tries to sell electricity and fails to meet its target, it must pay a penalty price that goes into a fund to support those industries that are making those changes. So this one comes with teeth, unlike the Kyoto Protocol, which says here is the target, but there's no penalty if you violate the target, no significant penalty. In the case of these commitments, there are significant penalties. So if you fail in the US to meet this, the failure is, the enforcement cost to you is about 40 US cents per kilowatt hour. I don't know exactly, I guess that's about 80 florins per kilowatt hour. So it's a pretty serious, maybe, no, I'm sorry. I think around 80 florins per kilowatt hour. It's a very significant price that you have to pay if you fail to meet the target. I'm going to go through a couple of other examples, but again, I just want to give you an overall picture. There are a whole series of principles and programs in which localities have made commitments to participate in climate action. And U.S. cities are very important parts of that, as are U.S. states. Most of the U.S. cities have in place climate protection initiatives. I'm going to show you a couple right now. And several have state commitments as well. So I'm going to again try to show you how this bottom-up process has been working in this regard. So let me go to San Francisco. San Francisco has a population of about, I forget, Gödöllő's population.
30,000. 30,000.
30?
30,000.
30,000. So it's very small.
It's a small town.
Yeah. So so San Francisco is probably maybe about 60% of Budapest population. something like that. If you live in this city, there is a requirement that the city reduce its release of greenhouse gases by 2012, the next year, by 20%. That's faster than what's required to get to the equivalent of 450 parts per million. This plan is on course. In fact, the city of San Francisco will meet this goal this year, rather than waiting until next year. It has also invested through a very interesting relationship with its citizens. It's invested in biogas, in new solar, and in new wind. The new wind is not located in the city, it's located in other parts of the country, but this is investments in the actual plant to bring about new renewable energy sources. The city has created a $100 million investment pool for energy efficiency projects, and currently in the city, if you wish to put up renewable energy sources, the city government will pay 50% of the capital cost in order to incentivize you to begin installing this kind of equipment. So the city, while the central government is not doing very much, the city is actually ahead of the game and getting us toward that 450 parts per million strategy. The city of Boston is a city of Chicago is a very interesting city. This is a population that is about, I guess, close to twice what Budapest is. This city also has a 20% target. It is requiring that the city itself power 20% of its electricity needs from renewable sources. It has set up an $800 million city fund to support the investments. It is the city with the largest amount of green roofs in the country. And I think very importantly, rather than knocking down its historic parts of the city, these bungalows are small homes that are where a great large percentage of Chicago are housed. Instead of simply doing away with those, they are now protecting them by giving them the incentive with energy efficiency and renewable energy sources for their needs. So about 10% of the city's residential population is now the focus of this particular program. This is an initiative that is mostly important to low and moderate income families. These neighborhoods are neighborhoods where people are working, well, except for a bad economy where nobody's working, but they aimed not at sort of the fancy buildings, but instead aimed at what is the more durable change that is needed in the city. Okay, so these are examples of how leadership is taking place in the United States. Again, the problem is that there is no central systematic effort to make this happen. Instead, local markets, local communities are leading the way. I'm going to give you now an example that comes from my own state that shows you how this kind of thing, though, can go toward solving a problem in a very big way. But to do that, let me first give you a general sense of the problem of energy inefficiency. When you look at climate change, and as I suggested, 50% of the improvement toward reducing that future world threat of climate change, about 50% of that is going to come from energy efficiency. How can this be possible? How can we cut 50% out of the energy needs of an industrial society? Between 1960 and the present, the U.S. increased its electricity use per person by a factor of 4. We use 4 times as much electricity in the end of the 20th century and the beginning of the 21st as we did in the middle of that century. So it looks like really hard. How in the world can you do this? But actually, there are significant models where this has been done. And one of those is in the U.S. The state of California made an important policy requirement. I was asked earlier about markets and how to get economic investment in energy efficiency. Here is a very practical way to do it. California told its electricity sector and its natural gas and other energy providers that they had to follow the following policy. If it is cheaper to invest in energy efficiency at the residence, at the factory, at the commercial building, at the farm, you must spend your money first there. If it's cheaper to do that than it is to supply energy, you must first invest in those options. When California made that rule in 1978, it flattened its electricity consumption per capita. Since 1978, California has not increased its consumption, and as an economy and as a place to live and as a population, California has the same problems that other parts of the U.S. have right now, but it is no worse by far because of this commitment. In fact, in some ways, California is better off today because it has less of its meager income in a big recession, has less of its income devoted to paying its energy bill. Europe is better than the U.S. best case right now. The European Union's per capita consumption is about 1,750 kilowatt hours per person. That is sizably lower than California. And in this sense, investments in energy efficiency have an opportunity in Europe that could be even more interesting than in the U.S. We still have a long ways to go. Depending upon how you count the gases, you're somewhere between 60% or 80% below 1990 that you need to get to. So all of us are still going to have to cut out a lot of energy waste in this regard. But it is possible for us to do this. And let me show you why and how it's possible. And this is where I think, on the question of economics and markets, where this new future is going to come from. So if you look at the U.S. and you ask how much will it cost you to buy a unit of electricity, the price in different parts of the country varies by these thin blue bars. The top of the bar is what residential customers pay, the bottom of the bar is what industrial customers pay. Okay? So this is how much it will cost you to use electricity. These blue wide bars are how much it will cost you to save the same unit of electricity. This is the amount to use, this is the amount to save. This is based upon 12 years of data of programs taken from around the country that were implemented bottom up at the local level. These programs save electricity at about 1/3 the cost of supplying electricity. The reason that California was so successful is that that margin difference meant a lot of investment went toward energy efficiency instead of energy supply. If the U.S. were to take advantage of this, it would mean that you are now able, through the savings from the electricity, to pay off the entire cost of investing in energy efficiency. While it is very difficult to figure out how we're going to cut so much carbon dioxide out of our future, if we have an approach where it will be cheaper for you over the course of the use of that equipment to save energy than it will be to use energy, and that saving will be large enough to pay the entire capital cost and interest and other things that are going to be associated with that cost. If it will pay for all of that, you then have the possibility of transforming the energy sector. And this is where I think there is some of the greatest opportunity for the future. So I'm going to give you an example of something that we created. It is a law in Delaware, my state, in Vermont, and in Washington, D.C., and it's being worked on in other places, including in China. It's called a sustainable energy utility. This sustainable energy utility creates a relationship between you and a series of companies that says, I will guarantee you, with money, I will guarantee you that I will save you energy, and the entire investment cost of saving that energy will come from the guarantee itself. That is, you don't have to go out and figure out all this stuff about where do I save energy and how do I save energy and all the rest. An expert audit system is done. That expert audit system then has a guarantee behind it that says that the amount that you will save in money will more than make up for the cost that it will take for you to improve energy performance in your building, in your vehicle, and the rest. Will this work? This summer, in August, the sustainable energy utility, which has existed for all of 1 year, went to the capital market and received $73 million in capital investment for this particular approach. That's a significant amount of money for a brand new entity that has only existed for a year. What I'm now going to show you is what happens over the course of this investment for the community, for the state of Delaware. It takes roughly 3 years for the investments to be made. This was all in public buildings, so universities participated, state offices participated, schools participated. This is entirely investment in public buildings, again driving down the long-term cost of those buildings and at the same time reducing carbon emissions. The investment created 1,000 new jobs. By the third year, the state's energy use is down by almost 10%, and its savings in energy cost is also about 10%. This was a 23-year investment process, so by the time this investment is done, the state will have cumulatively saved $121 million on a $73 million investment, and it will receive a net of $27 million. That is, the state not only gets paid off all of the investment costs on the front end, but it actually ends up with a net saving of $27 million that it can invest in libraries, in hospital needs, and other kinds of approaches. This model allows us to begin to think about a change in the energy sector that doesn't require us to all be poorer as a process. It actually requires us to shift away from depending upon energy use and toward energy savings. It recently received important news in this regard. One of the great values of going this approach is that if you invest in energy efficiency and conservation, job creation is about 3 times faster than if you invest in the old energy system. So you're going to give the money one way or another. You can either give it into here and get much less of an economic impact, or you can put it here and get 3 times the impact on jobs. Renewable energy is 4 to 5 times as much. Making our use of information and communication technology as a way to better improve efficiency and performance, that's the real winner. That's up in the vicinity of 6 times as many jobs that are created. And if you do this, something important can happen in your world. So let me close with this point. There is a country that does understand this challenge. This country is China. China no longer thinks about carbon and about energy simply as a question of environmental security only. It is integrating this into the economic base of the society itself. So I want to show you the world that we now face for the future. This is Shenzhen. This is a fishing village across from Hong Kong in 1980. So 1980. This is Shenzhen today. 2 New York cities created. 2 New York cities created in 30 years. It's just unbelievable, the rate of change. What is in Shenzhen? Shenzhen is home to the solar photovoltaic industry. This is the use of a technology that converts sunlight into electricity. It is the principal manufacturer of solar cells in China. Is in this city. And how important is that? In 2 years, by this model, 2 years by this model, China took over as the largest manufacturer of solar cell technology in the world. Solar cells are not a simple technology. It's a fairly complex technology. This is high-end with pretty significant job creation that is in the higher salary jobs. China has integrated this whole process of a clean energy and a low carbon opportunity into its policies, making it so that it can go. I gave you a very fast case of the sustainable energy utility in the US. China is in some ways going even faster. It is creating what will be this next generation model for us to get out of the problem of high carbon to transition in a positive way to a low carbon future. So I know I gave you some scary bits in the front end of this talk, that it's very difficult, the problems that you're facing, but I also want to close the talk with the premise that there are some very promising opportunities for how we can make this work in the future. Thank you very much.
The Professor, thank you very much. It's a really interesting presentation. I have to say that the part of the Chinese-related part of the presentation was very short, yes. And therefore, maybe if somebody has questions, don't hesitate to take it, because the professor will answer for it. So, if somebody has a question, please take it.
And I would like to ask you, okay, everything is okay with China, but you know, they invest in a lot of huge coal plants and still going on with something incredible, you know, and that would be my question. What could we do with it?
Yeah, the question is on China is at the same time that it's investing in the low carbon energy future, the low carbon economy, it is also investing in the high carbon energy future economy. And it is true. China is building a lot of coal-fired power plants. It is making some commitments to industries that are very carbon intensive industries as well. China is a mixed bag, and I don't think there's, so I don't mean to give you the position that China is only one thing. It is both. It is both part of the problem and part of the solution. What I was hoping to suggest to you is that the solution elements can go fast. In fact, maybe able to go faster than the problem elements. And so if you look at the sustainable energy utility in the US and you look at the China case of investment in new renewable energy, it's possible to make very rapid and significant change. How we will balance that, how much of it will be high carbon versus low carbon, it's not clear at this point. China is basically negotiating that path on the basis of what it thinks it can have as a comparative advantage moving forward in the 21st century. It doesn't have a lot of advantages left in the high carbon economy. It continues to invest in it, but it doesn't have a lot of long-term advantages. It does have significant advantages in the low carbon. As I say, in 2 years, this country went from supplying 11% of the world's solar energy supply to now it's actually above 60%. That's a good thing for the rest of the world too, just so I want to make also clear, because it is a complicated issue, but I want to make solar electric technology cost about, before China entered the market in this significant way, cost about $5 to $6 US, so over 1,000 florins, maybe 1,200 florins per watt. Today, it costs less than $2. It's somewhere south of 500 florins. So that means that all of us are going to benefit because that solar technology that used to be so expensive is now beginning to go down, and it will be more widely available for use in the future. So I don't know how China will play it out, which way it will tilt. My guess is that it will, because it has such an advantage in these areas right now, that it's going to go after the low carbon future. But we'll have to see. The US could do the same thing. It's a mixed bag. Europe could do the same thing. It's a mixed bag. Latin America could do the same thing. It's a mixed bag. Africa probably in some ways has some of the most extraordinary opportunities because of leapfrogging opportunities, meaning that in the case of South Africa, some of these old industries still have a very significant hold on the economy. But in other parts of Africa, these old Nigeria, but most do not have encumbrances in that old industry sector, and they may have the possibility of leapfrogging, not having to worry about what the cost is to give up that high carbon economy that existed in order to get to the low carbon economy. So. Other questions?
Sorry, we only have time for one more question. You can need to leave the next program.
One more question, please.
Thank you, Professor, for your presentation. In your presentation, you told or you explained the huge potential in energy efficiency retrofit projects, especially in the US. But my question would be, why isn't it happening actually?
Yes.
What are the reasons behind that?
Yeah, this is more in the realm of how you structure policy and economics. In the case of California, it is happening because the investment process was directed to energy efficiency so long as it is the cheapest option. The basic problem, I think the same thing is true in Europe. The energy efficiency is usually delegated to the energy sector itself, to utilities, to run these programs to promote energy efficiency. So a utility gives you a rebate to buy a better performing light bulb or something like that. But that is really counterproductive to that energy sector. Your utility largely makes money by selling you more electricity, not by selling you less. So it's not going to make a lot of investment in helping you to use a lot less. It's just a basic conflict in the business model. The reason that we have proposed the sustainable energy utility is it only can operate. It's a non-profit organization in the US. It only can thrive and operate if it saves you energy. It cannot make any money on selling you more energy. So we think that one of the reasons that the problem exists is the basic economic structure. Right now we have only entities that are committed to making money by selling you electricity rather than saving electricity, or selling you natural gas rather than, and so on. So if you don't create those new institutions, the EU trading scheme could do this in a way. If you set the price of carbon high enough, it would now bring into the market those new players. But the problem is that you have to set the price really high. And I don't see that the countries of Europe are willing to vote for such high prices for carbon. So my suggestion is, rather than doing it by making it more costly that way, why don't you do it the other way? Utilize the savings, the things that would actually make your energy needs and your energy bill go down. Why don't you make that the basis for the new economy, rather than simply pricing only the other. And to do that, you've got to invent new institutions. You can't simply wait for a carbon price signal to make that happen. Is that helpful? Is that clear? Okay, well, I think I'm told one.
So thank you very much again. I suppose we have left a lot of questions. Maybe we will invite you next year. And thank you for the audience. You can download the full version of the presentation for the Climate Council website, and you can follow the details. Maybe you can contact with the professor by email. You will get the releases. Okay?
Yes.
Thank you very much. Thank you for your attention. We will meet the next time. Okay? Bye bye.